So I would like to welcome all of you in person and also over the Zoom to Professor Alois Lugstein's talk. So it's my great pleasure to introduce Alois. So he's from Vienna Institute of Technology at Vienna, connected to Institute for Solid State Electronics. He did his PhD. Is it in chemistry? Like in the LinkedIn, it shows chemistry. But
PhD was chemistry, yes.
Okay, I see. Chemistry. I was like, not sure if it's chemistry or physics. Okay. So he got his PhD in chemistry from Technical University of Vienna. Is it the one that's in English translation? So he got his PhD in 1998. I was able to find the thesis title, PhD thesis title, hydroisomerization and hydrocracking on bifunctional catalysts. And later he moved to Vienna Institute of Technology, as I mentioned, and his work is covering Metal-Semiconductor-Metal heterostructures for electrical, optical, and plasmonic applications. And he's also working on some monolithic superconductors and semiconductor quantum circuits, I guess maybe connected even Nobel Prize prizes. Yesterday I was like hearing that it was also related to superconducting circuits for quantum applications. So we are very happy to have you, Alois, here, and really excited to hear your talk.
Thank you, Hatice, for the kind introduction and for the invitation. So giving me the opportunity to talk about a very old story, because what probably sounds fancy, metal semiconductor heterostructure, is nothing else than a Schottky junction, which is probably one of the eldest and best investigated semiconductor devices at all. But I hope I can convince you that by making use of a novel fabrication step, one can end up with this nice heterojunction. This one is shown here. This is a silicon aluminum heterojunction. And if you have such a Schottky junction with a high quality, high crystallinity, you can make use of that for applications in electrical, optical, plasmonic, as well as quantum applications. So for those of you who have never been in Vienna, we are relocated recently. We are still in the heart of Vienna, so 10 minutes from the St. Stephen's Cathedral. This is our nano campus Gusshaus, which hosts all the labs, offices, and a small clean room. Gusshaus means casting house, and the reason for that is that initially this building was made for fabricating weapons. That means casting weapons, and then happily they moved on to make statues like this. And so when you walk through Vienna, you will always see some of these statues, like our Empress Maria Theresia, Prince Eugene from Savoy. They were all casted exactly in this building where our institute is now situated. So in 2017, it looks like this, and then 2025, it looks like this. Some of the old parts has to be protected. Exactly this hall where the furnaces were stored is now a lecture hall, and some ventilation system in the basement. We also have a lot of furnaces, and one of these, namely the CVD reactor, was used to make nanowires. So Christoph Schöndorfer and Matthias Steinmeier were my first two PhD students, and they introduced the VLS mechanism, so the growth of nanowires, the bottom-up growth of nanowires, using a catalytic particle. So we use gold, then you introduce the respective gas, for example, silane, and that is dissolved in the gold particle. It supersaturates the gold particle, then you grow a nanowire below this particle. So these are a few examples of the nanowires that we have grown. So we have a freestanding germanium nanowire. This is a carpet-like growth of silicon nanowires. We've grown heterostructures, intentionally kinked nanowires, and so on. To make devices thereof, you have to integrate them in the device architecture, and therefore we harvest the nanowires. So by ultrasonification in isopropyl alcohol, and then we deposit the nanowires on an oxidized wafer, and we make electrical contacts by e-beam lithography, sputter deposition, and lift-off techniques. And what you see here is an individual silicon nanowire that is connected to gold electrodes. And as this is formed on top of an oxidized wafer, this device resembles a so-called backgated field effect transistor. So you have the source contact and the drain contact to the nanowire. Applying a gate voltage via the backgate substrate, you can accumulate or deplete the nanowires, and thereby you can control the transconductance of this nanowire. To make reliable contacts is a really important part when you think about devices. And Thomas Burkhardt spent some time on making quasi-metallic contacts on a germanium nanowire. So what you've seen here, and I hope I can start it once again, is a germanium nanowire that is connected to two copper pads. And if you heat up the structure, you see that these bright extensions are formed, which arises as the copper is diffusing into the germanium nanowire, forming a copper-3 germanide, which appears bright in the SEM. And happily, the interface in between this quasi-metallic copper-3 germanide and the germanium is abrupt, more or less atomically abrupt. So by that, you can make nice contacts. This behaves like a metal. And you can control the length of your device without any expensive lithography, just by controlling the annealing temperature or annealing duration. And with that, you can make ultra-scale devices. You see what is shown here is the length of the remaining part of the germanium nanowire. So you can make a device with a segment length of 100 nanometers, 61, and down to 7 nanometers. And what is shown here is the resistivity as a function of temperature. And for this rather long device with 100 nanometer, this behaves nicely as a semiconductor. So you see resistivity decreases with increasing temperature due to the formation of electron-hole pairs. And if it gets shorter and shorter, particularly for the ultra-scale device with only 7 nanometer, there's no dependency on the temperature, which is already an indication of ballistic transport in this super short device. If you continue this annealing, the wire will be completely exchanged and you will end up with a copper-3 germanide nanowire. This is shown here, and this behaves already like a metal. So Sebastian Kral then tested a lot of materials. So at that time, we were interested in superconductor, semiconductor, heterostructures. And finally, we ended up with aluminum, So very same story, germanium nanowire, 2 aluminum contacts. And what is shown here is again, an in situ movie of this exchange mechanism. So this is a germanium segment. The germanium is diffusing into the enlarged pads and is replaced by aluminum. For this particular system, as you see in the phase diagram, there's no germanide, no stable germanide. So this is really a complete exchange of germanium by aluminum. And this is the image that I've shown in the first slide. This is the interface of the remaining germanium, which is single crystalline, and happily also the aluminum that replaces the germanium is single crystalline. So by this exchange mechanism, we can make very small dots, quantum dots, which are connected in a self-aligned process to real metal contacts. And Maciej Sistani made use of this and made devices of different segment lengths and did a very simple experiment. Namely, he measured the IV characteristic of these devices with different lengths and varied the channel from about 2 microns down to 10 nanometer. And thereof, he calculated the resistivity, just the inverse of the slope, plotted this resistivity as a function of the segment length. But what you expect is, according to Ohm's law, that it is directly dependent on the length. However, if you get shorter than 45, 50 nanometer, you see there's no longer any dependency on the segment length. And the reason for that is that the mean free path of electrons in germanium is about 45 nanometers. So we definitely enter the regime where we have ballistic transport even at room temperature. In addition, these nanowires were really thin. Happily, the Bohr radius of germanium is quite large, and the spacing of the subbands is rather large, much larger than these 25 milli-electron volts, which corresponding to room temperature. And therefore, we were able to observe quantum ballistic transport at room temperature for these germanium nanowires, the one that is shown here. You see nicely here this plateau at G0 of 1, and even the waterfall plot shows these quantum ballistic transport behavior. If you cool down this structure down to 10 Kelvin, this germanium dot remains like, oh no, what we've observed is finally Coulomb blockade. In that case, the tunnel barriers are formed by the depletion layer in between the metal and the semiconductor. So if you cool it further down, below the transition temperature of aluminum, the aluminum gets superconducting, and you enter the regime where you can control the supercurrent through this device by an electrostatic gate, which is nothing else than a Josephson transistor. So all this was done with exactly the same device, just cooling it down from room temperature 10 Kelvin down to 450 millikelvin. This can be even improved a little bit if you take a particular type of nanowire, a so-called core shell nanowire. So this is a germanium nanowire, which is surrounded by a silicon shell. And thereby you form a 2D gas at the interface with a higher mobility. And thereby we were able to see several of these plateaus, which are formed at the integer of the quantum conductance. Okay, then Corona pandemic came over us all, and we have a lot of time to read papers thinking about what we can probably do else with these structures. And the idea came up, probably we can make use of this aluminum for plasmonics. The nucleus was this simple experiment where they shined on one end of a silver nanowire, and they observed that light was emitted on the opposite end. So the plasmons are excited here, propagating along the silver nanowire, and finally decay radiatively at the opposite end. So we deposited now this structure, or we transferred this structure on a thin membrane, as it is shown here. That was a 30 nanometer thick silicon nitride membrane. And in this membrane, we patterned a focus grating coupler with the focused ion beam. And the idea was now that we excite some plasmons in this grating, which are propagating along of this aluminum nanowire, and then they should decay at this germanium interface, and we can somehow detect the hot charge carriers which are generated here. So the simple experiment was then that we were scanning with the laser along the structure, and we measured the current in between these two pads. So this peak, when we are on top, at top of the germanium segment, this is just photocurrent. So the light excites electron hole pairs, and these can be detected. But we get an additional current peak when we're at top of this grating. And the idea is of what we suppose what happened is that we start plasmons. The plasmons are propagating at this interface. And at this interface, these plasmons decay in hot electrons. And those with an energy higher than the Schottky barrier can make it over this barrier, traverse through the germanium segment, and can be detected as a either plasmon-induced or photon-induced current. So I've shown you before that we can tune the length of this segment by this annealing process. And the idea was now, can we combine these ballistic transport with the decay of the plasmons? So the idea was we launch a plasmon, plasmons are propagating, decay at this interface, are injected in the germanium, and now they traverse through the germanium ballistically. So that should finally lead to a really fast detector. And together with Juraj Damo from the Photonics Institute, we made these cross-correlation pump probe measurements. And indeed, we've seen that we have, I don't want to state that we have a super fast detector, but at least one of the mechanisms in these decay of the plasmon is super fast. So that will probably enable detectors with the bandwidth beyond 1 terahertz. Okay, we have super fast detector probably. We have nice quantum devices. Anyway, this handling of the nanowires is laborious and very time consuming and not scalable at all. So we tried to transfer this process on germanium on insulator wafer. That means we started with a thin layer of germanium on top of an oxidized wafer. Now we patterned the nanowires or the nanosheets, added the aluminum contact, did the annealing, and here you see some examples. Indeed, it's one and the same device after different annealing steps. So it works the very same way then for the nanowires. And also here we can do an ultra-scale device close to the mean free path of the electrons, which seems to behave as a ballistic device. So now we are no longer restricted to these rod-like one-dimensional structures. We can make whatever we want. We can make tapered structures, king structures, tripods, band structures, and even these van der Pau structures. So these are different steps of the exchange process. So here just the connections have exchanged. So here it's the exchange is going on, and here almost all these van der Pau structure is exchanged. So if you continue further a few minutes, you will have a thin aluminum sheet. And these structures we are currently using for hopefully sophisticated quantum devices. Currently we are working on this one, so we want to reproduce the nanowire driven devices. So we will now control if the nanowires made top down behave in a similar manner than the bottom up grown nanowires. And then we are thinking about some squids, multi-terminal devices, freestanding devices, or some quantum dots which are interacting. That should all be possible with this new mechanism. Currently we are in the stage where we have performed the first device, so this one, and you see some first results that they indeed show very similar results than that we observed with the bottom-up grown nanowires. So with this top-down approach, we can also make now thin sheets, starting with the silicon on insulator wafer. This can be easily thinned down by common oxidation, so that we end up with about, in this case, 4 nanometers thin silicon layer, which is automatically passivated by the oxide. And then we make these aluminum contacts, do the diffusion, and we end up with a very thin aluminum sheet. So here you see the test structure, this bone-like structure. Here part of the structure is exchanged. This is still silicon. Here we have a full exchanged sample. This is the cross-sectional view. So for this device, we have an aluminum sheet which is about 4 nanometers thick, which is also proven here by the EDX investigations. And by that, we can now, in a very similar way as we did it with the length of the segment, we can now tune the thickness of this aluminum sheet by these oxidation steps. So we can make sheets which are 20 nanometers thin, 4 nanometers thin, 1 nanometer thin, which is the thinnest up to now. And a nice feature of these structures, which is not well understood now, is that when these sheets get thinner and thinner, the ampacity, so the maximum current that you can drive over these structures before they fail. So finally they crack, get one crack. It's not that they explode, they just get one crack. This ampacity increases when the sheets get thinner and thinner. And compared to what was predicted in the ITRS roadmap, you see that we are about 2 orders of magnitude above these critical current capacity or the ampacity for aluminum. So what we expect for these thin sheets is that we have a change in the transfer of the electrons through these sheets by a modified electron phonon scattering, which is somehow proven by these very recent noise measurements. So you see that the 1/f noise decreases by about an order of magnitude when these layers get thinner and thinner. And the reason for that may be that these sheets are single crystalline. So in the common metallization scheme with aluminum, we have polycrystalline aluminum. You have this bamboo structure with grain boundaries, and these grain boundaries are mainly the reason for the failure. Another nice feature which we also don't understand up to now is that when we cool these thin sheets down, we saw a transition or an increase of the transition temperature. So the thicker layers, with about 20 nanometer, get superconducting at about 1.5, 1.6 Kelvin. If we get thinner and thinner, and this is the thinnest one that we achieved up to now, this transition happens at about 2.8 Kelvin. So, as I mentioned, these aluminum sheets or aluminum wires are single crystalline when they are narrow. So the wider sheets are polycrystalline, but as soon as you get below 500 nanometer widths, you see these are single crystalline aluminum sheets, and they are really smooth. So the surface is extremely flat. That was again the point where we intended to make use of that for plasmonic devices, and Zhao modified the process in a way that he just patterned holes into these sheets before the aluminum deposition. And when you do then the exchange reaction, these holes, which are formerly situated in the silicon, are then situated in the aluminum. That works quite fine. Here you see the SEM. So this is after 4 minutes annealing. So the bright part is still silicon. So this is already exchanged. And if you continue for further 8 minutes, these tranches then in the aluminum. And again, you end up with a very sharp interface. So also on this side, finally, we'll have sharp interface, and these hole also positioned in the aluminum. What for do we make these holes? So these were now planned to make use as a Plasmon coupler. And this is the structure. We have two aluminum pads which are sputtered. These are the holes or the Plasmon couplers. And when we do a scanning along this line, you see that we get a very small peak here, a larger peak here, then one in the opposite direction, and once again here when we are at the top of this hole. So this shows that again, this coupler works not as good as this focus grating coupler, but still we got some small signal. Anyway, this one is larger than this one. The reason therefore is that the propagation length is much shorter here than here. So we did a detailed investigation that we made these devices where we kept the length of the germanium segment constant, but we tuned or we varied the length of the aluminum waveguide. This is shown here for red and green light. And you see that the current, of course, increases with the length of the plasmonic waveguide as you have more and more damping and you lose the energy of the plasmons. And that means you generate less hot electrons at the interface. Very same device, but now the aluminum was kept constant and the germanium segment length was varied. And here you see nicely that the current increases when the germanium segment length decreases. That means that the device gets more and more sensitive when it's shorter. So it is proportional to L squared, to the length square. So intentionally, you should make a very, very short device with a very short aluminum waveguide. So this is what we've done here, because here we excited the plasmons directly at the interface. So to say the waveguide length is 0. We did the same cross-correlation measurements to get an idea about the temporal behavior of this device, about the speed of the device, and we investigated 3 different devices with 3 different channel lengths, a rather long device, 2.4 microns, 1.3 micron, and one less than 100 nanometer. And in the cross-correlation signal, we have 3 different regimes with 3 different slopes, which corresponds to 3 different time constants. We have a very fast process with a few picoseconds time scale. Then we have a region which is directly correlated to the length of the segment. This is the transfer time. So the plasmons are propagating here along this waveguide. then they decay to the hot charge carriers, which is a very fast process. Then they have to traverse through the device, which is a region B, and finally region C, which is has a very long time constant. This is related to traps in the devices, so they're not well passivated. We have a lot of traps, particularly on the devices which were based on germanium. Okay, so then again, say how did the following nice experiment that he made use of the backgate voltage? There's mentioned at the very beginning that this aluminum silicon contact is a Schottky junction, and the Schottky junction has a particular barrier high. So it is well known that aluminum is pinned about mid-gap, so that means we have a barrier of about 600 millieV. And anyway, for the green laser, the electrons will easily surpass this barrier. So they have an energy of about 2 eV, so they can easily surpass this barrier. Anyway, if you change the backgate, you will bend the bands either downwards or upwards. And if you apply a positive gate voltage, you will bend it downwards, and that means you will block the holes, and you will preferably inject the electrons, and that means we detect a negative current. Even at zero bias, so for an unbiased device, you measure a negative current through this device, which is just a result of the injection of charge carriers with the momentum in this direction, and they will surpass this silicon segment. If you change the backgate voltage to negative backgate voltages, you will bend the bands upwards. Now you block the electrons, and you will preferably inject the holes. So we detect a positive current. Again, even at zero bias, you see a positive current. And then he wanted to get control over the two barriers individually, and he made two contacts directly at top of the interfaces. And with that, he can emulate the PN junction. And if you have this device without any excitation, it indeed behaves like a diode. And if you shine light on the coupler, again, plasmons are propagating, they decay. Now you can control if you inject electrons or holes. And you see exactly what you expect for a photovoltaic device, but now it's not that you harvest light, but you harvest the plasmons. That's in principle what we would like to call a plasmovoltaic device. And now you can play around with the backgate voltages, and you can really control if you inject holes or electrons. And if you apply the same voltage on both electrodes, that means that you have more or less flat band conditions. Here you inject the same amount of electrons and holes, and you get no current because the electrons compensate the holes. Okay, so we can control the barrier high. That means that we can probably also detect light with an energy less than the band gap, because the electrons must only surpass the barrier. So we don't have to excite electron hole pairs, which is 1.12 eV. In silicon, we just have to lower the barrier below the energy of the light that we want to detect. So if we change the backgate voltage, we will bend it downwards, and lower energetic electrons can be injected into the channel. So that means the barrier changes from 600 millieV to about 250 millieV. And a postdoc of mine, Mauro, is working on this mid-infrared detection scheme. And he investigated a 7 micrometer laser. And the only thing what he did is, it's the very same device that we used for the green laser experiment. So sorry for this one, it's exactly this device. And he changed the gate voltage, sorry. And you see that if you are above 15 volts, you get a nice signal out from a 7 micrometer laser. It's linear dependent on the power of the exciting laser. And it's really fast. So we did the same cross correlation measurement. This is now for telecom wavelengths, but still above the band gap energy of silicon. And we get a time constant of about 3.7 picoseconds. That will, but it corresponds to a bandwidth of about 200 gigahertz. And finally, what he did is that he inserted this detector in a FTIR system to detect the characteristic lines of water vapor. And this is a comparison with of the ALCL photo detector with a reference detector of FTIR. And you see that we have a perfect fit with this reference detector of the FTIR. Yeah, with that, I want to close. So I've shown you how we fabricate these Schottky junctions, these Schottky junction devices, which we can use for quantum devices, for hopefully ultra high speed photo detection. So we know that the mechanisms in this device are really fast. We transferred this on a wafer scale platform, used it for plasma voltaics, and currently we are on the way, hopefully, to a device that enables mid-infrared detection. With that, I would like to thank funding agencies, cooperating partners, and I would like to thank you for your attention. Thanks a lot.
Thank you, Alois, for the nice talk. Do we have questions either from audience here and front? Okay, there you go.
Yeah, thank you very much. That's very interesting. Yeah, I have a question. Like, again, maybe one of the simple questions. Did I get wrong? Right, that when you hit the samples with germanium, just evaporating and escaping the germanium from the nano just escaping somewhere?
Yeah, not somewhere. It's this. The germanium is diffusing into the aluminum pad. So these pads are huge. This is a nanowire, let's say 100 nanometers thick. This is 150 times 150 micrometers. And the solubility is about 1% of germanium in aluminum. And we did a very simple experiment. We made this pad very small, 1 times 1 micrometer. Then you see an exchange up to here. And as soon as you have 1% of silicon dissolved in the aluminum, this process stops. So then you can heat it up for hours. So the interface will remain at the same position. And so you have to guarantee a huge reservoir where you can dissolve the germanium.
Germanium penetrates into aluminum?
Yeah.
Not the aluminum.
No, this is happily the diffusion coefficients are so different. So we tried to do all these experiments that I've shown here with this nickel approach or copper approach, but unfortunately they diffuse into the silicon and the germanium and they get completely contaminated. And the nice feature of aluminum is that you see the diffusion coefficients are 10 orders of magnitude different. So the germanium or silicon segment is absolutely pure.
It's huge, 10 orders.
Yeah.
I have another one. So when you show the dependence of the current, when you have the excitation of the plasmons, which are propagating and vary the barrier against. So should this barrier, I mean, the feature on the IV curve, yes, the feature on the IV curve here should correspond to the energy of the excited laser which you use. Like, for example, if we change the wavelength of the laser, should the feature, I mean, for the gate voltage, shift somewhere? Since, I mean, the energy of the plasma changes, so you need to bend the gap somehow differently.
Sure. As soon so for the green laser, the energy of the electrons is somewhere here.
Yeah.
So you cannot block them completely.
Yeah.
The point where you get zero current is the point where you inject the same amount of holes in electrons. So when you assume you have flat band, then you inject this same amount of holes and electrons, then you have zero current, but you still inject, so the plasmons decay. When you do these experiments with the light with an energy less than the barrier high, and this is shown for the 7 micrometer, then you can really completely block the current and you inject no charge carriers.
So if we imagine that we tune packets, the source. So if you tune this laser, so this the threshold should shift.
Exactly, yeah. Yeah, exactly. It shifts in this direction, yeah, or depending on the wavelengths.
Yeah, actually, just that one. So, depending on how much line should very much diagram, but then like high energy, plus, especially if it exceeds, and then the edge of the tunnel comes with a small barrier, then it's not for wavelength specific as far as I understand, and maybe even more than that, it's that has mid-hour protection. How can you discriminate from just having the energy coming from the it's because they have much higher really fast.
Yep. Very good question. We got the same question from a reviewer. But we did a really nice experiment now, so which hopefully can convince the reviewer and you, also you. So we have this device. So we modified the devices a little bit, that we have we made them a little bit wider, and we made a real trench. And then we did the excitation with the laser of different polarization. So when the polarization is along of this trench, we can not launch effectively plasmons, but we introduce the same. So he was asking, is it really a plasma or is it just heat? Because if you heat it up on one end, you will also get some injection. But with this,
like heating, like
thermal heating, yes. So the laser power is rather high, but with that experiment now, I hope we can convince him. So if we do it, if the laser is polarized in this direction, we got almost no signal. It's polarized in this direction, where you can effectively launch plasmons. You get a really nice. And we have the same laser power in both experiments, so we can exclude the heating, and with that, I think it's that we really have fun.
One more thing is when you had this strategy creating devices, I think you mentioned this spatial silicon creating silicon inside there. Always the thickness of the size thing of thermal procedures. Yeah, for
Okay. This is already on a wafer scale, so we can make use of a lot of materials. So we have one pad in addition to the structures, and we control the thickness of the structure by ellipsometry. So we can, first of all, we control it by the oxidation duration. So we go in 1 minute, we oxidize 100 nanometers. And if it's not, you don't have the proper thickness, you use it once again.
But I mean,
It's thermal oxidation. Thermal oxidation at 900 feet.
you can take it out with ellipsometry, then take back distance.
This is the real nice feature. So if you make a 1 nanometer thick aluminum sheet, you can do it in an ME system, but if you put it out, it's immediately oxidized. These devices, they're stable for. I mean, we made them a year ago, and they.
But this 4 nanometer, you measure ellipsometry. This is 4 nanometer at the step B.
Yeah, finally, you see, we send it to cooperating partners into a TM. And the thinnest one, I don't know if you have a TM, is now 1.4. That is now already also proven by TM.
getting right, that there should be a monomer on the lower surface? If so,
so probably you realized it already during my talk. We are absolute beginners in Plasmonic. I know that you can have these long-range surface plasmons, and the guy to whom we sent the TM sample said, "Why don't you investigate exactly what you mentioned?" So if you have a 1 nanometer thick aluminum sheet, which actually has the same medium on top and below, that you're of interest. But yeah, we can only make use of our segment as a detector. So for these investigations, you need probably 2 microscopes where you excite on one side and detect how much light you can couple out on the other side. I think for detailed investigations, our detectors are not that great enough. But I fully agree. I think it's a nice platform to do these investigations. Yeah.
Thanks for the talk. I have a simple question. All your aluminum in this talk is crystalline aluminum?
No, unfortunately not. I want to show you this one. So with the nanowires, with this bottom-up grown nanowires, which were 100 nanometers thick, they were single crystalline. We made this really nice materials. For these aluminum sheets, which we formed from the SOI or germanium insulator wafer, we've seen, so for the thicker sheets, you see, this is 2 micrometers thick. This is the remaining germanium, this is the exchange part. You see that you have grains of different orientation. If you get thinner and thinner, and you see this is about, I don't know, 1 micron, so it's almost single crystalline, but as soon as you're below 500 nanometer, even these sheets, which we form from SOI or germanium, so for some reason, if they get wider, then you have some, I don't know. I mean, I'm wondering at all that they're crystalline.
So this is only works for the crystalline aluminum. So what happens if you use it by the anomalous aluminum?
Amorphous?
Yes, amorphous.
You mean amorphous germanium?
Aluminum.
You mean sputtered aluminum?
Yes, but by E-beam evaporation.
I don't know. I mean, happily, we have a monolithic structure. You see, normally you deposit the metal on top of the same structure, but now we are really a monolithic structure, which is not easy to create if you do sputtering. So we've never investigated if we got similar results.
Okay. I just wondering because if you use it by the E-beam evaporation or sputtering, so the aluminum should have the high velocity.
I expected. Yeah. I mean, particularly the smoothness of this aluminum. You see, this is the sputter layer, and this is the exchange layer, and even there's a difference in the scale part. So this is really, I mean, it has the same quality than the commercially available silicon wafer or aluminum. But I was asking if you're talking about amorphous germanium, that this process of the exchange. So what we did is that we sputtered germanium. So and the exchange works also for amorphous layers.
Is it the same quality?
No. You don't have the sharp interface, you get that much.
May I ask you also something? When you have this exchange of the atoms, is it happening like in inert atmosphere or it is air?
We do it in forming gas, so 10% hydrogen and nitrogen. But it works, as you've seen, we have this this in situ movies, it works in vacuum for sure.
said in that image, I forgot the panel D, when you have very thin layer. So at that point, it is aluminum is crystalline. When it's really thin.
Is the width?
The width, I
Yeah.
mean, that way you were shooting, right? It was thick, and then the width, not the length, but the width.
Yeah.
So at certain width, it becomes single crystal.
Below 500 nanometer, yeah. So the grain of aluminum is typically in the range of 1 micron. So
Okay,
as soon
when
as
it
we're
gets
below,
smaller than that. But then that reduces the detectivity power, so that's why you prefer to have a bit wider detectors.
so it's not possible to make the 100 and 100 micrometers. This will polycrystal.
But what happens if you have multiple disconnections?
Exactly, that's we do it. That we make several of these channels.
And you collectively end up with the total current.
Exactly.
Question maybe from audience, if you have, you can unmute and ask. Okay, no one? All right, if not, I would like to thank Alois for this very nice talk.
Thank you.